Hello, I'm Yi Jiangguo from Peking University. In this presentation, I will introduce our recent work, Pillars, an integrated CGRA design framework. Following is an outline of this presentation. Firstly, I will discuss the background of pillars. Secondly, the introduction of pillars will be given. Thirdly, I will show the capabilities of pillars to model various CGI designs through an experimental study. Finally, I will answer some excellent questions about pillars. First of all, let me introduce the coarse-grained reconfigurable array, CGRA. CGRA is a class of reconfigurable architecture that provides word-level granularity in a reconfigurable array, and has a faster reconfiguration process than FPGAs. An example of a typical CGI architecture is shown at the bottom left. The CGRA consists of an array of processing elements, and each processing element has a reconfigurable functional unit, and some reconfigurable routing units like multiplexers. CGRA provides the capabilities for spatial, temporal, and parallel computation, and hence can outperform common computing systems in many applications. Like the example at the bottom right, CGRA takes advantage of time multiplexing resources to perform computation. The tools for the exploration of fine-grained FPGA architectures is mature, while CGRA design and exploration tools remain in an embryonic period. Two core requirements have not been completely satisfied: iterative optimization of hardware implementation and design space exploration. Some existing frameworks and tools may be helpful. CCF can simulate acceleration of loops of general-purpose applications on CGRA, but it does not provide synthesizable RTL codes. A Stanford CGRA toolchain can rapidly create and validate alternative hardware implementations, but it is loosely coupled and has low adaptability for various CGIs. CGI-Me permits the modeling and exploration of a wide variety of CGI architectures, and also promote researches on CGI mapping algorithms. However, its RTL generator becomes brittle when iterating the logical implementations. So we develop pillars to better meet the needs of CGI design and exploration. The key features of pillars are integration, flexibility, and consistency. The open source repository of pillars is also shown in this slide. A detailed introduction of pillars will be presented in the following slides. This is the overall pillars framework, where components and data flow between them are shown. The yellow portions represent tools or actions in our framework. The blue portions represent middle results during runtime. The gray portions represent inputs in a specific format. Taking integration into consideration, the major tools in pillars are developed based on the Scala programming language, a widely used host language for developing embedded domain-specific language. CECO, a Scala-embedded hardware construction language, Place the law of RTL generator in our framework. There are four main parts of our framework. The first part is the description and the extraction of an architecture. We propose Scala-based architecture description language (ADRES) for CGRA designs as an initial input. The ADRES of CGRA is passed by an architecture interpreter, producing a hierarchical abstract model of the CGRA architecture. To obtain a high-quality representation for mapping, and reduce the complexity of RTL generation, the hierarchical abstract model will be flattened. The flattened abstract model in device will produce corresponding basic chisel models and the modulo routing results graph (MRRG) to model CGRAs. The third part is the hardware generation. The auxiliary models will be automatically generated depending on the regions of basic models in the hierarchical abstract model to support cycle-accurate simulation, and the interconnection will be realized. As a result, we will gain a chisel-top design. And lastly, automatic generation of Verilog RTL will be carried out. The third part is the mapping and scheduling. Mapper receives the data flow graph (DFG) for a specific application as input, as well as the MRRG, to map the DFG onto the CGRA. And the scheduler will reconstruct the schedule of mapping results. Together with the hierarchical abstract model, the products of mapper and the scheduler can be translated into context that will be applied in simulation. The first part is the RTL-level simulation. We implement a component that aids simulator code generation. With the help of Chisel-I/O tester and the validator simulator, we can obtain the result of cycle-accurate simulation for functional verification. Now I will introduce our ADL. We employ a hierarchical design and a flattened implementation method in our framework. Only the basic elements of architecture are still corresponding to hardware models, while redundant nodes and layers will be optimized. Blocks and elements are basic components in our ADL. Blocks are able to represent the hierarchy, and each element shares a particle ID with corresponding chisel hardware implementation. A block can be composed of several sub-blocks and elements. There are 5 alternatives of predefined elements: multiplexer, const unit, arithmetic logical unit (ALU), load store unit (LSU), and register files (RF). This is an example of the ADL. A block contains a multiplexer, an ALU, a constant unit, and a sub-block with 2 input ports and 1 output port. All blocks and elements are identified by names, and if they share a collective parent block, their name must be different. Each block can have any number of input and output ports through function calls. Connections between parent blocks, sub-blocks, and elements can be added in a particular form. Elements have some parameters to define the hardware specification. To generate hardware, basic chisel models, also called explicit models, will be generated with the flattened abstract model at first. Auxiliary models are automatically inferred to add reconfiguring and running applications correctly. After the wires are connected, a chisel top design is produced, which can generate the RTL code and enable cycle-accurate simulation. According to the parameters set up in the ADL, an explicit module can be generated with different data weights, sizes, logics, and so on. There are three kinds of auxiliary modules. Config controls can repeat stored configurations and distribute them to corresponding explicit modules. To control the cycle modules should fire, we employ the schedule controls to fire ALUs and LSUs when operators are mapped onto them. Synchronizers can implement synchronizers input for explicit modules with more than one input ports. Before presenting the mapper and the scheduler, I will briefly explain the terminology of the inputs of them. The data flow graph DFG is a graph representing the computational data flow. There are two kinds of nodes in DFG. The OP node is a node in DFG, representing a computational operation. The value node is a node in DFG, representing the data. The modulo routing resource graph MRRG is a graph representing the hardware resources and the structure. It is a 3D hardware resource graph extended in the time domain. The func node is a node in MRRG that implements an OP node in DFG. The routing node is a node in MRRG that transfers a value node in DFG from a func node to another func node. A module can be translated into a directed graph with these nodes. We can duplicate and modulo the graphs in the time domain to get MRRG. The target of mapper and scheduler is to produce contexts that guide reconfigurable modules to perform correct behavior during reconfiguration. The mapper can map every OP node in DFG to a specific func node in MRRG, and map every value node in DFG to a connected sequence of routing nodes in MRRG. Our mapper is an integer linear programming server mainly based on an existing work. The file time and the synchronization method of each operator are determined with a scheduler using topological search. To simplify the simulator code generation, we define three processes of programming: pre-process, activating process, and post-process. In the pre-process, the input data stream is transferred into LSU through direct memory access, and the contents are read by the top-level CGRA module. After the top module is enabled, the activating process starts, and the auxiliary modules are fired. Explicit modules can perform routine or operations set by config controls if they have been fired by schedule controls. In the post-process, we can get the output data stream from LSUs. As shown in this figure, a few templates and tools in Pillars are useful to construct the simulation process and produce classes in the specific format of chisel. The expected behaviors of CGRA can be verified at the output ports of the top module during the activating process, or the data obtained from LSU during the post-process. This is the project tree of pillars. In the example subfolds, user can try the example of end-to-end flow, or examples of mapping and simulating various applications on an architecture. In our study, we model 4 CGRA architectures with 2 architecture skeletons and 2 P designs. We use variants of ADRES architecture skeleton. LRUs in 4 Ps can perform a full set of operations: add, subtract, multiply, shifts, and OR and XOR. LRUs in reduced Pes can only perform add and subtract. The full architecture has torus connectivity. Ps in the same row share a block with a load store unit. Similar to the original ADRES architecture, Ps in the top row share a global IF instead of a local IF. Simple P consists of 2 multiplexers, an LRU, a const unit, and a IF with 2 registers. Complex P has 2 additional multiplexers for bypass. We target the Xilinx JC706 in evaluation board using Vivado 2019.2 for physical implementation. Considering the performance and the resource distribution, we interleave 2 neighboring P columns, and the blocks with LSU are located at the center during Floorplan. This is the layout of FPGA implementations. This table shows the maximum frequency and the FPGA area breakdown of the implementations, as well as the success rate of mapping within 7,200 seconds for benchmarks in an existing work. The resource usage of both explicit modules and auxiliary modules are reported. For architecture with reduced skeleton, benchmarks with many multiplication operations cannot find feasible mapping within the time limit. Since there are only 10 multipliers and has no torus connection, we select 2 excellent questions in Q&A part. The first question is, can there be several connect LRUs in one PE? Of course, yes. This is one of the core strengths of pillars. Users can design their P blocks with arbitrary connection and hierarchy. The second question is, what is the overhead of using pillars? The auxiliary modules may introduce overhead. The configuration controls are necessary for reconfiguration and have fixed and slight overhead according to the architecture. Users can determine the scale or abandoning of schedule controls and synchronizers in a global config file, so the overhead of them can be controlled. Researches about a better trade-off between the overhead and the function of auxiliary modules are in our schedule. Thank you for listening.